Okay, so this is the last lecture on tensor methods. So I hope in the last 2 days you got a good idea of what tensor methods are about, how we can go about applying it to a variety of different latent variable models, and how we can analyze these methods, right? So, I mean, kind of the idea is, although these are non-convex problems, they have a lot more structure than general non-convex problems. So we are able to provide guarantees. In particular, the main property is that when it can reduce it to a tensor form which has no spurious local optima. So you know that any like say gradient ascent kind of method would converge to a correct solution, and that's why with these tensor methods we're able to provide guarantees that we can consistently recover the parameters. And we saw that we could handle a wide range of latent variable models. Kind of the main intuition is like, the statistical constraints, especially conditional independence constraints, gives rise to additional information about the distribution. And this is reflected in tractable forms in the moments, right? So if you write out the tensors, you can reduce it to tractable forms. And that was the main kind of overall view of thinking about a range of different latent variable models in a unified viewpoint. So today I'll be talking about more practical issues like, okay, so I have this method that can compute these parameters. How does it work in practice? And in particular, how does it compare to other methods, right? And how do I scale it up to large data sets? So I'll talk about some of our experiences. First on a single workstation. We've also implemented on GPUs, and these methods are in fact perfectly suited for GPU operations. And most recently, we've been looking at a cloud-based implementation on Reef. And you've seen lectures by Marcus, and that's going to continue this week, on how to do implementations on Reef. And these tensor methods are also very well suited to be implemented on this platform. And this is still ongoing work, but I'll give some insights on what we've found so far. So just to recap the basic tensor factorization method, what we had was looking at, let me start with the toy example we had in the first lecture. So this was the topic model with just 2 topics, and there was only the single topic in each document. And I just showed in this toy example that there were just 3 words in the vocabulary, right? So this was the multi-view model that each document had 3 words, and there were just like D was also equal to 3, so I had 3 words in my vocabulary. And the multi-view assumption was that all these words are conditionally independent given the topic. And my estimation goal was to find these topic probability vectors, which is the probability of different words under different topics, right? So this was a D by K matrix, and I wanted to estimate this matrix. And this was just the sample code I showed to generate the samples. And once I had the samples, we computed the second order moment, which is the co-occurrence of 2 words in my documents, in the set of documents. I'm asking on average, what is the probability of co-occurrence of any 2 words in the vocabulary, right? So I'm going to compute this empirical moment, and then we did rank K SVD on the second order moment to obtain the whitening matrix. So the intuition of whitening was to implicitly change the system, right? So originally I had these vectors here, A1 and A2, in D-dimensional space, and they're not orthogonal in general, but I'm going to convert it into an orthonormal system in K dimensions. So this whitening step reduces the dimensionality from D-dimensional space to a K-dimensional space. And as we are doing it, we are also making it an orthogonal system. And so that was the idea that the first operation is SVD. So I'm going to do a rank K SVD, and K is usually small in our applications, but we'll see how to, again, scale it up to like large amounts of data, like when D is large here. So keep in mind, this is the first step. It is to do SVD. And once I have the SVD, I'm going to compute these whitened samples. right? So I'm going to reduce my samples from d-dimensional space to the k-dimensional space. And once I have this, the idea is to now operate on the tensor with whitened moments, right? So this is now the third order tensor, which is the co-occurrence of 3 words in the vocabulary, but then I'm whitening the tensor. So now I'm computing this empirical moment using the whitened samples. And the power method we saw in the last 2 lectures, you can think of it as gradient ascent for the problem of maximizing the Rayleigh quotient. Right? And this is just a simple multilinear operation. So you take these samples, and I'm computing this inner products with my current estimate of the eigenvectors, and I'm normalizing it, and I'm kind of continuing this operation. And this was the idea that the power method recovers these eigenvectors. Right? And so this was the power method, right? So I'm doing this quadratic operation, I'm normalizing it, and once I converge, I'm going to subtract out those estimated eigenvectors, which is the process of deflation, and I repeat again. And we saw that in practice that this, for the simple example, that there is fast convergence to the eigenvectors. Right, so this was just the toy example, but now if I want to implement this on a large-scale data set, on a real data set, what are the optimizations I need to think about further? How do I ensure that it becomes scalable to a large-scale data set? So that's what we will see today. Right, so in particular, we've looked at 2 applications, and mostly I'll be focusing on the first one here in the talk, which is the task of community detection. So yesterday I showed you how we can employ the tensor methods for learning communities, hidden communities in networks. So we saw this, there is the classical stochastic block model, which posits that, there are nodes which belong to different communities, and the probability of an edge is only dependent on the underlying communities, right? All the edges are conditionally independent given the community memberships. And then there is the extension we saw to mixed memberships where nodes can now belong to multiple communities. These are the so-called mixed membership stochastic block models, and we saw that the tensor methods can also be extended to the framework where now nodes can belong to multiple communities. Right? And so today we want to look at examples where the size of the network can be up to some millions. So I'll show the instance where on a single workstation we can handle graphs with millions of nodes. And our goal is on the cloud, we can even push it further. We can, make it as large as just requiring more cores, so we can parallelize it to a large extent. And the communities, usually we think of them as a few thousand, right? So typically we want to mine for a small set of communities from this graph data. And similarly, you could think of the topic model setting where the size of the vocabulary is usually few 100,000, maybe up to 1 million. And you have a large number of documents, usually millions of documents, right? So this you can think of them as samples, like how many samples you have. And again, the number of topics you'd like to mine is usually a few thousand. So the question is, how do I handle this scale, right? So the main challenge is this. Here in the graph setting, it's the size of the network, which is large. And in the topic model setting, the number of documents and the size of the vocabulary are large. So how do I make it scalable through this setting? And that's what we'll see today. Okay, so the main papers on which the talk is based on, so this paper, like my students, Farong Huang, Niranjan should be in the audience somewhere here, and Mohammed. So this we, did it last year, and an ongoing work on implementation of Reef. We still don't have the write-up out. We are still running the experiments. So in that, my student Farong interned at the Redmond lab, the Microsoft Redmond lab. Sergey is also involved in the project. There's Paul and Nikos who are also involved in this project. And the CPU and GPU codes are available on GitHub. I guess the title got cut out here, but you can check my website for the full code. So the codes are available, and we soon plan to release the Reef code as well. So that'll be available online as well. Okay, so let's now just recall the tensor method for community detection, and then see how in each step we can incorporate techniques to make it parallelizable and scalable. So, just to recall from yesterday, what we had was this notion that these communities are groups of nodes, and then there is kind of a common connectivity pattern between nodes in the same community, right? So the simplest case is this stochastic block model, where nodes just belong to a single community, and here there is more connectivity within a community rather than outside. And we saw that with mixed membership, now you have nodes belonging to multiple communities, and you have this varying connectivity based on how they belong to different communities. And kind of the common unifying notion is that all these edges are generated conditionally independently given the community memberships. And we are assuming that these community memberships are drawn from a Dirichlet distribution, right? And so depending on the concentration parameter of the Dirichlet distribution, we have varying amounts of overlap in the communities. So this is the generative model, but my task is that given the graph, I'd like to recover the community memberships. Right? And if you recall, the idea was to now mine for particular subgraphs in the counts of these subgraphs by partitioning the nodes and looking at like these star with 3 leaves, right? How they occur across the partition. So the very first step was to just divide the nodes into 4 sets. And I said that in theory, it's fine to have random partition, but in practice, you'd also maybe want to optimize for having a large number of edges across the cut. Because there are if there are more edges, there's more information about the communities they belong to. And the idea is for every triplet here, I'm counting how many common neighbors are in this outside set X, right? So that was exactly this count here that I'm looking at for every triplet A, B, C, how many common neighbors are present in X, right? So G is the adjacency matrix. So I want to have edges, all these 3 edges present. And then I kind of count it as an S and how many such nodes are present. So I'm summing over X here. And this was a tensor form of the same object. So this is a 3rd order tensor of size equal to the size of set A times the size of set B times the size of set C. So this is a tensor of order n cube, right? So because n is the number of nodes in the network. And this was the main idea that once I had this partition nodes and I looked at the set of edges to each of the subset A, B, and C, this formed a multi-view model. So conditioned on the community membership with node X, all these set of edges, right, into these 3 subsets are conditionally independent. And also each one is a linear model. So that's why we could reduce it to this multi-view linear model that I described yesterday. And to recall, the main 2 moments we had to compute, right, was the 2nd order moment, which required essentially counting for 2 stars, that is between say A and B. I'm asking how many 2 stars are present between them. That's essentially this pairs matrix, right? And then I'm symmetrizing it, so I'm kind of doing some pseudo-inverse operations and some multiplication operations. And then I'm forming the 2nd order moment. And I'm also doing a 3rd order moment where I'm looking at the symmetrized versions of my neighborhood vectors, and I'm taking the outer product of them to get a 3rd order tensor. Right? So we're going to be operating on these 2 statistics. And the theoretical reason is that in expectation, these are multilinear forms of these unknown vectors U, right? So the second order moment is a bilinear form in the UIs, and the third order moment is a trilinear form in the UIs. So this is the theoretical justification of why we consider these moments. But now let's just review the operations we are going to do on these statistics. So we have a pairwise statistic, which is a n by n matrix, right? So order n by n. And the third order one is like an order n cube object. So we're going to be operating on this. And just to recall the tensor method, what we're going to do is compute an SVD, in fact, a rank k SVD of the second order moment, where k is the number of communities. So for now, I'm going to fix k, but in practice, you can also do cross-validation. You can try different values of k and see which one has the best perplexity or some score that you're interested in. So yeah, there's also a way to estimate k, but for now, let's fix k. So I'm going to do an SVD, rank k SVD of the second order moment. I'm going to whiten the third order moment to obtain this tensor, which is k cube, right? So I've reduced my tensor from n cube object to a k cube object. And then I'm going to do the power method, right? So what we saw was to do the power method on this whitened tensor, but we'll see in practice there are different versions I can do, right? I could do like stochastic gradient descent. There is like alternating least squares method. So there are various ways to do the decomposition, the orthogonal decomposition of my tensor T. And then finally, we need to do the post-processing because I've only decomposed a k cube tensor. So I need to recover the communities from this information that I have, from the eigenvectors and eigenvalues that I've recovered. I need to get back the communities. And finally, we need to see how to compute the error scores. This could be the perplexity, or which is the version of likelihood for the model, or if ground truth is available, we can also validate against it. We'll see that in many of the examples, there's ground truth available, so we can have alternative evaluation criteria based on that. So this is just a rough overview of the techniques, right? So let's first focus on the first step, which is whitening. So this requires the SVD operation. So what we need is, so first, even before SVD, I need to do some symmetrization, right? So I needed to compute first this pairs matrix, which is an n by n object, and then I need to compute some pseudo-inverse, and then do these multiplications. So even in just this step, if you do it naively, it's possible to go wrong, right? Because what I have is an n by n object, and n is like millions or even more. Then even storing this and doing the product, right, is not scalable, right? So right now we are just thinking of running it on a single workstation. So we want to optimize for both space and time as much as possible. So so this was the operation, right? So if I had to do like manipulations on like n by n objects, right, take the pseudo-inverse, even just storage, like for instance, if I had like a million nodes, and in general, we'll see that graphs are sparse. So the pairs matrix by itself is a sparse matrix. But on the other hand, if I computed the pseudo-inverse and tried to store it, that's a dense object. Right? So, and if I just simple calculation of the memory, it says that I would need like about 58 TB to store these objects if n is a million. Right? So if I did this naively, this is not at all possible to do it in a single workstation. Just the simple operation, right? So this is just the very first step of the tensor method. But then, we know that the pseudo-inverse has structure, right? It's rank k. We are only going to do like kind of rank k representation of these pairs matrices and then manipulate them to get the pseudo-inverse. So my pseudo-inverse really is like of this form where it has a rank k representation. So instead of like kind of, so my storage is now, right, it's much more promising because I have to just store nk objects, right? So the space complexity is just n times k. And typically just this pairs matrix, it's just n times s, where s is the sparsity level, right? So think of like the sparsity of every row. So usually these graphs are extremely sparse, so I'll never run into an n square object here. Right? So I can store just the pairs matrix by themselves as like, because they are sparse, I can still store it in a single workstation. But the problem was to store inverses of these matrices which are not sparse. But then I know that I only care about the rank K approximations, so I'm going to store it as a rank K approximation. And so that is still manageable in a single workstation. It's about like a few GB instead of like, TBs. Right, so there is just a very simple, trick makes a big difference in these operations, and that was one aspect. But it's still like for computation, right? So in order to do these products, I can also like kind of essentially just order the products in a different way. So like the intermediate quantities that I'm storing is also now just n by k objects. Right? Never n by n dense objects, because now this is still like an n by k, this is an n by k, this is an n by k. Right, so just, this is quite, I think, simple to see in retrospect, that when I have to do these multiplications, I have to manipulate them as, like, these pseudo-inverses in terms of, like, their rank K approximations. And I have to do the multiplication in kind of the right order to ensure that I store only n by k objects. So that's why we can, handle with a small amount of space, even like, matrices up to 1 million by million, which are sparse, we can handle them in a single workstation. Okay, so I've, now computed the symmetrizations that are needed. Now I want to do the SVD. Right, so again, if I did the usual like rank K SVD of an n by n matrix, the computational complexity is n squared K, right? So which is again not scalable if n is millions. But there are there's a whole range of randomized low rank approximation techniques. In particular, I'm just mentioning a few here. Indeed, this is a very exciting area of research on how to come up with fast randomized methods and how we can make it, how we can get. So you won't be getting the exact SVD, but there are even theoretical guarantees of getting good approximations when the K is reasonably small. So for instance, what we can do is I've just shown one method here, and I've just shown like two possibilities. If the pairs matrix is dense, you would just sample a random matrix, for instance, with Gaussian entries. But if we know that in the applications we are interested in, we have this matrix to be a sparse matrix. And in that case, what we're going to do is do like column subset selection. This is the paper by Clarkson and Woodrow. And so I'm going to just like randomly select columns and put random signs on them. I guess this is plus minus 1, so this is so with a random sign here. And so once I get these only subset of columns, so think of like the number of columns I choose. This k tilde is like a few times k, right? So k is usually thousands. So if k is 1,000, I'm going to choose it like say 2,000 columns or 3,000 columns. So I'm going to choose a few more, like some factor of the rank that I want to estimate. And so this is my matrix M2 times S, right? So these are randomly selected subset of columns with random signs. And I'm going to find an orthogonalization of it. So this is the Gram-Schmidt orthogonalization, for instance. And then I'm going to compute this matrix Z, which is just a k by k matrix. So I'm going to reduce my n by n matrix to just a k by k matrix. And I only need to do SVD on this k by k matrix. right? So I don't need to do the full SVD. I'm only doing SVD of a k by k matrix. And then there are just some simple manipulations to compute the SVD of like M2, right? So this V is like the set of singular vectors, VM2 for the original matrix M2, and L is the set of singular values for the original matrix. So it's a very simple set of steps. I'm doing some either multiplication or like selection to get a tall thin matrix. And then I'm doing reducing it to a k by, I'm doing orthogonalization, and then I'm reducing it to a k by k matrix, doing the SVD of this k by k matrix, and then again projecting it back to this n-dimensional space. Right? So now it turns out that the computational complexity of this randomized method is much better than the computation for exact SVD. So if the sparsity level of each row is S, and I have like C cores, it is NSK by C plus K cube. Right? So this K cube is coming from doing the SVD of this K by K matrix. Right? So it's K squared times K, which is K cube. So when usually K is small enough, this is a fixed cost that you have to pay. But then you can parallelize all the other operations, right? As long as you have enough cores, the other operations become almost irrelevant. So as you have larger number of nodes, you just need larger number of cores to handle the operations. And so almost like this first step is the bottleneck. And indeed, we have access to a large set of techniques to do fast computations for SVD, right? So when I want a low rank approximation of a large matrix, I can have a whole range of techniques, and I've just shown one possible technique to handle this. So that's how in the first step we can get this computational complexity, which is essentially K cube, right? If I have enough cores. So it's independent of the number of nodes if I have enough cores. So this was the whitening step. So once I've whitened it, I want to now do the tensor decomposition on the whitened samples. Right? So I had this M3 object, which is, this D should be N here. So I have an N cube object, but instead I'm reducing it to a K cube tensor because I've done the whitening. And I want to do a decomposition of this K cube object. So the method that we saw before, for conceptual reasons, this was easy to study, as well as like the analysis of the error buildup was easier to go about, is this power method with serial deflation, right? So I'm recovering the vectors one by one, and I'm serially deflating them. But then in practice, it's much faster to do them in parallel. Right? So if I have to wait for each vector and then subtract it out, then do the other, it can be slow. So an alternative technique that is employed quite extensively is this alternating least squares update. So here what I'm doing is I'm fixing I'm going to introduce these matrices A, B, and C, right? And I'm just trying to minimize this objective function, right? So I want to find these decomposition with components A, B, and C, right, which fits my tensor T. And then in each, it's called alternating least squares because I'm going to fix two of the modes. For instance, I'm going to fix B and C. I'm going to update A. Right? And we know it's linear in each of these variables. So if I fix B and C to update A, it's a simple linear operation. It's least squares. So I can do this efficiently. And so I can cycle between fixing two of the modes and updating the third one and go about doing it. And this is what we implemented on the cloud, so I'll come to this method a little later. But still, when the number of nodes is large, if I did this as a batch, this is expensive, right? So there are two possibilities. If I had to, if I didn't compute this tensor, for each pass, if I had to compute the sum over all the nodes, right, then this is expensive. The other option is to form this tensor and store it. And if I have enough memory, I can do it if k is not too large. Otherwise, this also becomes expensive. So this is if I did this as batch, but I could also do it as a stochastic update. So here I'm never forming this tensor explicitly, and with each new sample, I'm just updating my gradient, and then just touching just one sample at a time. So here this GA is like a Whiten sample of my neighborhood vector to this subset A. And similarly, I have these Whiten samples here. So, and I'd like to think of optimizing this objective of finding a set of vectors that fits my empirical tensor. Right? And I've used this parameter theta to think of like a trade-off between an orthogonality cost and a correlation reward. Because the intuition is I'd like to have these set of VIs to be orthogonal. So so with this I would only get like rough orthogonality, but in practice that suffices, right? So I don't need to maintain a strict orthogonality. And this is much cheaper to do. So I'm going to put as I increase theta, there is a much more advantage in having orthogonal vectors. And at the same time, I want to have vectors that are well correlated with my set of, like the empirical tensor. So I'm balancing between the two. And so on this objective, I can do a stochastic gradient descent. And to do this is exactly the gradient. So this is my update in each step. Beta t is the step size. And you'll see that the operations are essentially just inner products. Right? So in each step, I'm getting a new sample here. This is GA, GB, GC. These are the Whiten samples. I'm computing inner products with the current estimate of my vectors, right? Set of vectors, VIs. And then I'm just updating them. Okay, so think of this as like a set of, have these Whiten vectors here. I'm like, computing inner products along this set of fixed directions, right? These VIs, right? And then I'm also computing like a set of inner products among the VIs themselves, right? And the idea is that if the VIs are mostly orthogonal, this term is small. And if the VIs are well correlated with the samples, this term will be large, right? So that is the balance between maintaining orthogonality and also having good correlation with my empirical tensor. So I can do this trade-off, and so you see that in practice, I don't have to form the tensor explicitly. So I'm just taking a new sample, I'm computing the gradient, which is essentially this multilinear form here, right? And then I'm doing the update. So although it's the decomposition of a tensor, the advantage is you never have to form the tensor. You don't have to form and store the tensor, so it becomes scalable. Okay, and that's why in like the space complexity, you only need to like maintain like kind of k-square objects, right? Because there's I have like in dimension k, I have k eigenvectors, and that's all I need to maintain, right? So I'm only storing those, and the time complexity is like if I had C cores, it's k cubed by C for each iteration, because I'm doing these k-square inner products, right? Because I have to compute k-square k-square entries, and each inner product is like order k, because I'm doing an inner product in k dimensions. So you see that this is, again, when k is small, this is in fact very negligible. And in fact, I don't even need too many cores for this step. So the first step is mostly the bottleneck, which is to compute this SVD of an n by n object. Right? So, and that we can do with randomized techniques. But after that, the tensor decomposition with stochastic gradient is extremely fast. And the very last step, once I've found the eigenvectors and eigenvalues for my Whiten tensor, I have to get back the community memberships. So I won't go into all the details. There's some normalization parameter that's required here. You can refer to that in the paper. But the idea is if I have this set of eigenvalues and eigenvectors from my, from the stochastic gradient operation, and G is my adjacency matrix, I essentially have to do some simple, matrix products to get back the communities. And typically in practice, we'd like to threshold the values because I want sparse memberships, right? I'd like the nodes to belong to a few communities. So I'm going to do some thresholding after I do these operations. So again, these operations are fully parallelizable because these are just products, right? Matrix products. And again, if it's sparse matrices, you have even better efficiency. So if S is the sparsity level per row, you have like NSK by C. So if you have sufficient number of cores, again, you can make it fully parallel. And in the end, we are storing just like these community vectors for n nodes, and each one is k dimensions, so it's n times k. Right, so this operation, again, can be made extremely fast. Yeah, so that's kind of the overall, space and time complexity for the tensor method by first using the randomized SVD techniques, maintaining rank K approximations for computing the symmetrizations, then doing stochastic gradient on my Whitening tensor, and then doing like a final post-processing where I get back to the n-dimensional space, but that's some simple matrix product operations. So you see that the overall time complexity, if I had enough number of cores, is essentially just an SVD of a k by k matrix. So this is k cube. And the other steps are very, they're in fact very fast in practice. And here I've also in the column just shown the comparison to the stochastic variational approach. So Dave Bly's group and Eric Zing here. I mean, a lot of researchers have been looking at variational techniques on the mixed membership stochastic block model. And there, the main kind of quantity for complexity is the number of sample node pairs. So this could be as large as as n square, because n square is all the node pairs. But in practice, they find that you can do it by sampling just a subset of node pairs. So think of m as between like n and n square. And so in each iteration, I have this complexity, which could be as large as n squared times k, right, in the worst case. And again, parallelizing this, again, there's a lot of exciting research going on, including here at CMU, but it's still, like not as straightforward as parallelizing matrix and multilinear operations. Right? So with matrices and tensors, I argue that is a very big advantage that parallelization is trivial, right? Almost all the operations are just embarrassingly parallel. So, and that's I would argue is a big strength of these methods. Yeah, so now let's, so I'll talk about some additional optimizations we did on the code, and also how we went about looking at different data sets and what are the validation mechanisms. So we did both GPU and CPU implementation. So in fact, this method is ideal for GPU implementation because the GPU has a lot of cores which are very simple cores, right? So they can handle only simple operations, but we also need only simple operations. We only need either matrix products or some kind of inner product addition, like simple BLAS operations, right? So they are ideally suited for GPU implementation. But the downside is that the memory, right? So the GPU memory currently is extremely limited. I mean, I think it's mostly like the reason behind it is that the technology hasn't yet caught up. Like there are a lot of these machine learning applications which can now benefit from a lot more memory, and I think that will happen in the coming years that we would have GPUs with a lot more memory. But currently, this is in fact the major difficulty in implementing these methods on GPUs, because once I don't have enough memory on the GPU, I'd have to kind of do a lot of out-of-core operations. And in that regard, the libraries are still not, sufficiently developed. So I think there's a lot of room for, incorporating like linear and multilinear operations on GPUs. But I feel that there is also a lot of work to be done in terms of developing still, good libraries. In fact, when it comes to sparse implementations, I think there is again a lot of room for improvement with GPU libraries. And in fact, it's kind of a non-trivial problem, because with GPUs, like how do you have a sparse representation and how do you communicate it to the GPU? I think there's still a lot of ongoing research. So what we did was we did a GPU implementation, but we only did it as a dense implementation, meaning that all our manipulations are assuming that the matrices are dense. So if they are, on the other hand, these graph the adjacency matrices are sparse, right? So we are not getting the benefit because of sparsity. So we also did a CPU implementation, but on CPU we have good libraries that do all the manipulations in sparse format. So we use the eigen library, and there are sparse, like you can do all the implementation in sparse representation, and that is also very important to get the to get us to work on a single workstation up to million nodes. So we could have, just store them as sparse matrices, do the manipulations in the sparse format. And so with respect to the GPU, like I said, memory was a bottleneck, so we had to carefully partition our data and kind of send them in blocks when the graph becomes large. So that was one of the challenges. The other challenge is for even iterative updates, right? So think of the stochastic gradient update. So what I'm doing here is I'm looking at whitened vectors, and then I'm computing these inner products, and I'm updating my estimate of the eigenvectors. So, but the challenge is each time if I, so the simplest way to code for a GPU, if any of you have done GPU coding, is the so-called standard interface. So here, what essentially the communication is handled in a standard way. So each time, all the variables that need to be computed are kind of communicated from CPU to GPU. The computation happens in the GPU, and then you transfer back everything. Right? So because I want to compute these eigenvectors, I have to transfer them in each iteration to the GPU and then back. So this can be quite expensive, and because I want to, and these eigenvectors are not too large, right? Because they're k-dimensional vectors. They're k vectors, each is k-dimensional. So that's why we can now do instead a device interface mode for this iterative operation, where I store the eigenvectors in the GPU itself. So I don't have to communicate the eigenvectors back and forth. And each time I'm just like, taking a new whitened sample from my CPU and updating these eigenvectors. And this, in fact, gives a big boost, quite a big boost compared to doing the standard interface. So this magenta line here is the so-called standard interface, and CULA is the library we've used. So this is the linear algebra library for GPUs. This is built on CUDA. So if I did the standard interface, I get this scaling, right? So the x-axis is the number of communities, right? So the k, like so I have like k eigenvectors, each of dimension k, and this is the running time. So you see that this is the magenta line with standard interface, whereas if I did the device interface, I get like almost like a 10-fold improvement in my running time. And the other, so this, of course, there is the standard MATLAB interface on the CPU. This is like the coldest, but like the toolbox for tensors, and that, of course, is, there's no competition, right? In fact, yes, the intention is not to kind of directly compare, but just I showed here as a way to see that it's pretty bad. And the other one is like the CPU implementation, which is like the eigen library. And that, again, like the GPU with the device interface is the best, which is intuitive because you have very efficient operations on the GPU compared to the CPU operation. So especially as I increase K, it would be much better to do it on the GPU. So, although we haven't done it, you can think of even hybrid implementations, right? You could, for instance, do like randomized SVD on CPU, maybe even on the cloud, and then you could do this, stochastic gradient descent for tensor factorization on a GPU. So if K is small enough, meaning K is a few thousand, you can still fit all these eigenvectors in a GPU. So and this then operation can be very fast. So there's a lot of interesting, engineering questions on how to kind of use the resources, say on the cloud, on local machines, on the GPUs to have fast computations. Okay, so these were some I think nice questions here also of how to minimizing the communication. So if I have both GPU and CPU, how do I minimize the communication? And we see that although the device interface was harder to code up, there are gains by doing that. So that was in terms of like the GPU implementation. And now we want to see that once we have carried out these operations, how do we go about validating it? So in the experiments that I'll show you, we have the ground truth information. So we'll see, for instance, we have information about, like, say, in a DBLP data, where the notes are the set of authors, right? And the edges are when two people co-authored a paper. We also have this ground truth of where the paper was published, right? And you can think of them as communities. So the set of journals and conferences as communities. Right? And then the question is, can we recover? So our estimated communities, are they close to these ground truth communities? So I have now an assignment problem of how to relate the estimated communities to my ground truth communities. So now we come up with a very intuitive error measure to compare these estimated and ground truth. So pi is the ground truth communities, pi hat is the estimated one. And so we'll do kind of a soft test. So we'll think of a notion of p-values, right? And based on that, we will do a pairing of how likely is it that this estimated community is related to this ground truth community, right? So I'll compute p-values, and then based on like the significant ones, I'm going to declare them as paired. So for instance, if these are like set of ground truth communities, these are set of estimated communities, right? They need not be even the same number of them. Based on p-values and thresholding, I infer a set of communities, right? So it may well happen that a community here may not even have a neighbor here, right? Because my p-values tell me that there isn't a statistically significant relationship between them. So I'm going to, and this is something I think is like some more, better motivated to do in terms of how to relate my ground truth to the estimated communities, right? So once I have this pairing, I can then compute the error measure based on like how do the entries differ in this paired set of ground truth and estimated communities. So here this set of edges here are the set of inferred edges based on p-values. And I'm going to ask like an L1 error for every estimated community and the ground truth community. Right? And the notion is that if I have a lot of false pairings, then I have a large error. Right? So I'd like to have a good assignment of my estimated to ground truth community, and their, the weights are also small. I mean, the difference of the weights is also small. In that case, I have a small error score. And so that's the idea that, first, when I have these estimated communities, I'm going to relate them to ground truth communities using p-values. And after I do the pairing, I compute an L1 score and normalize it suitably. So that is the evaluation metric. So now let's see how do we do in practice, right? What are the so we did it on a small network of Facebook with just 20,000 nodes, but we here had the ground truth information. So this was an anonymized data set where it was in a university, like what are the majors, what are the dorms, what are the high schools that people went to. So we had this ground truth information, and so this was interesting for us to check out, although this was a small data set. The biggest one we did was this DBLP, which is up to 1 million nodes. I mean, we also subsample them with 100,000. We also have results for that. So in DBLP, the communities are like the journals and conferences that people publish in. So we also looked at a kind of more recommender system setting, where on one side we have the set of users, the other side we have the set of businesses. So these were reviews on Yelp. And we are even ignoring the text of the reviews, right? We are only looking at whether there is an edge between whether a user reviewed a particular business. And we looked at the stars, so we did use it as a weighted graph. And so the first thing is the running time. So what we did was to run the variational code from Dave Bly's paper and compared it to our method. And you see that even on like a small network, there is in fact no competition, right? So this was just both on the same workstation using a CPU code. So there is a huge difference in the running time. That's because the variational method is very expensive. Like in each iteration, we have these expensive operations, as well as we need a lot of iterations, a lot more than typically that's needed for these tensor methods. So you see that there is a big boost in the running time, and in fact we can go all the way up to 1 million nodes on a single workstation. So it was just about like 1.5 hours to be computing about 100 communities on this DBLP data. So yeah, so we can so we have a good. In fact, a very big boost in running time compared to the variational techniques. And we also have very good error scores as well. That's the error score that I described in the previous slides. So since I'm almost out of time, I want to just, so in summary, we have now almost the best of both the worlds. We have good recovery accuracy, as well as very fast running times. So these, in fact, these are just simple linear algebra and like multilinear algebraic operations. So that's why we can have them be run very fast. Since I'm out of time, I won't talk a lot on this, on the cloud-based implementation. This is something we are just starting to do. I don't know how to go. So all I just want to say is just our preliminary experiments on the New York Times data set. We've seen promising performance compared to the stochastic variational technique, and compared to a simple like map reduce operation where it's very expensive to do iterative updates, right? So that's why you see that overall this is hugely expensive. Like if I had to do these iterative operations to get the tensor decomposition, like on a map reduce framework, it takes like 4 hours, which is ridiculous. But on the other hand, as I just have do a reef-based implementation, and as I have more nodes, I'm like able to get that to be very fast. And we want to now scale it up even to a larger cluster, and we hope to have it to be much better than the times that I've shown here. Okay, so concluding this talk series, what we saw was these tensor techniques have good theoretical guarantees, but you see that even in practice, these are easily parallelizable. They're scalable to large data sets, and also have good accuracy, both in terms of like good perplexity scores. I didn't show them, but they're available in the paper, and also like ground truth validation as well when we have ground truth. And so that's how I see these techniques as having a lot of interesting challenges in terms of theory, right? So how we can push them beyond in terms of especially learning overcomplete models and getting good theoretical analysis. And as well as in practice, you saw today, there are interesting questions of how to do a cloud-based implementation, a hybrid CPU and GPU implementation, how to come up with fast randomized techniques for processing on matrices and tensors. So I find it a rich set of questions here to look further into. Thank you.